Consider identical twins on the ground floor of the Empire State Building, each massing 55 kilograms of mass. So there they are at the bottom. Alice runs up 86 flights, reaching the height of 381 meters in 20 minutes. In so doing, her muscles must do work on her equal to her gravitational energy. Why? Because at the bottom she has no kinetic energy, and let's say she has no potential energy. At the top she has some potential energy, and if she's come back to rest, she has no kinetic. So this energy had to come from somewhere, and the only thing acting on her is her muscles. Why do we put it that way? Because the work done by her muscles is actually quite complex. The force is varying, its direction changes, it's complicated and time sensitive, and so on. But the work done by gravity, the energy that she has to put into it, that's really very simple. It's just mgh. And if we grind out the numbers, we get 210 kilojoules. Her twin Charlene decides to join her, but Charlene dawdles a bit. She takes 3 hours to reach the observation deck, still climbing the stairs. So the work done by her muscles on her has to be her mass times g times her height, but they're identical, so it's the same mass, and she's ending in the same place, so she also does 210 kilojoules by her muscles. It takes exactly the same amount of work to raise each of them to the top of the Empire State Building. Work doesn't care about the time it takes, and therefore energy doesn't care about the time things take. In fact, the point of the energy system is to not have to know what goes on in the interim. But, on the other hand, if you ran into Alice and Charlene at the top of the Empire State Building, you could probably tell which one had run up and which one had climbed slowly. To capture that time information, we introduce a new concept called power. Power is defined as the rate at which work is done. That is, power is the work over the time. Textbook prefers delta E over delta T, but since the work is what's giving us delta E, that's all the same, that's fine. The SI unit for power is the watt, symbolized by a capital W, named after James Watt, who invented the first practical steam engine. From the definition, we can see that 1 watt is 1 joule per second, which is 1 newton meter per second, which is also 1 kilogram meter square per second cubed. These two things are certainly valid and true, but very rare to run into. They're not particularly useful. Note the potential for typographical confusion. The work done is symbolized by W, but that's an italics W. And the power, which is the work per second, is measured in watts, which is a non-italicized W. In print, it's pretty easy because the variable will always be italicized and the unit will not, but in handwriting, you have to judge from context, and you need to be careful. Here we have a measure of world GDP per capita, which is basically the individual share of the world's wealth, more or less. And of course, it's been projected backward. We don't have actual numbers from the fall of the Roman Empire or whatever. But we can see that for most of human history, it was relatively flat. There is a slight upward slope, but it's hard to see on this scale. And the reason it's hard to see on this scale is that once Watt invents his steam engine, the wealth in the world takes off along this hockey stick, where it is many thousands of times what it was in, say, 1750. And this is largely because, starting with Watt and then moving on, we have learned to access more and more energy, which means we can have more and more wealth. Just to close the loop on what we were doing, the power exerted by each of the climbers were, well, Alice would be 210 kilojoules over 20 minutes, which turns out to be 170 watts. And Charlene would be the same over 180 minutes, because she took 3 hours, and that would be about 19 watts. This turns out to be a couple of light bulbs worth of power. This turns out to be about a third of a reading light bulb of power. If the force is constant and the velocity is constant, say pushing an object across the floor at constant speed, then the power is relatively simple. The power is the rate at which work is done, which is the force times the distance over the time it takes, but we can group the d over t together and make it the force times the velocity. So if they are constant, the power is just their product. If they vary, then the power at any given instant is their product. And we could say that the total work done would be the integral of the power times d dt. So dt. Again, if you haven't done any calculus, don't worry about this yet. It's not a thing we'll use in this class. But in principle, we could take each instantaneous powers and add them up. All right, 4 students run up the stairs in the time shown. Which student has the largest power output? We can do this without any kind of calculation because we're trying to rank them. So we can say, let's consider A versus B. Well, they go up the same distance, so they do the same total work, but B does it in less time. So between A and B, we know that A's power is less than B's power. And then we can consider over here, we can say, well, consider B and C. They go up the same distance, they take the same time, but B does more work because it's 80 kilograms times G times that distance. There's only 64 kilograms times G times that distance. So we see that B is greater than than C. And then considering B and D, we can say that the power rate would be the same if she had gone up only halfway in half the time. So we can take it to be 10 meters, but then only 12.5 seconds. But that's still more, and so we can see that B is greater than D, so B must be the most. Four toy cars accelerate from rest to the top speed in a certain amount of time. The masses of the cars, their final speeds, and the time to reach the speed are all noted in the table. Which car generates the greatest power? Well, for this, we're going to say something like, well, the power is the work per time. Don't get too put off. This is how I write capital P's just to keep them distinct from lowercase p's. You don't have to do that. It's just an oddity of my own handwriting. And then we can say, but the work done is going to produce a change in kinetic energy, which in this case is the final kinetic energy minus the initial, which is 0. So the work done is the final kinetic energy. So we can go back to the power and we can say this is really the final kinetic energy over the time, which is 1/2 mv final squared over the time. And then we just grind that out for each of these different ones. And we get the following. Here's our kinetic energies. Here's the power they take. All right, so this over the time gives us the power. In watts, we have something like 0.225 or 0.2, 0.2, 0.1, and 0.2. So we see clearly that it's case A that has the greatest power. Two little things to wrap up with. One, light bulbs are often rated in watts. You often hear someone say like a 60-watt bulb or maybe a 40-watt bulb for night light or something like that. And that's because historically, incandescent bulbs were manufactured in essentially one way. The incandescent bulb is the thing where it glows because it gets hot with a lot of current pumped through it. And after Edison more or less perfected that, basically everybody adopted that standard. And so all light bulbs took the same amount of energy to produce the same brightness. And so people got in the shorthand of saying, well, that bulb will consume 60 watts and it's X brightness. But on the other hand, there are many different types of light bulbs now, and many of them have much better efficiencies, so they produce equal brightnesses for much less energy or much lower power use. Watts is not a measure of light output, it's a measure of power consumption. Modern LED lights are as bright as traditional bulbs, but they consume about 1/10 of the energy, and they last about 10 times as long. All bulbs should really be rated in something called lumens, which is the SI for brightness, but no one does that. So if you go to Home Depot, you'll see the bulbs are rated in so-called watt equivalents. This LED bulb is as bright as a 60-watt incandescent bulb, etc. And finally, you might have run into the idea of power through the term horsepower, which you might know from, for instance, car engines. Turns out a horsepower, the power that one horse can deliver, is defined now internationally as 746 watts. It's a weird number because it wasn't picked to fit the metric system. It was picked to fit a bunch of British measurement units by none other than actually James Watt. Ironically, a typical horse cannot actually maintain 1 horsepower, although it can do up to 15 in a burst. Generally, it will do a little bit less for a sustained amount. And allegedly, James Watt deliberately undersold horses so that investors in his steam engines wouldn't complain if the engine was a little bit less powerful than he had said. I don't know if that's true or not, but it's kind of the story that kind of makes me chuckle. So.